So here's our first example for collisions and conservation of momentum. So we have a ballistic pendulum was used to measure the speeds of bullets before electronic timing devices were developed. The version shown in this figure consists of a large block of wood of mass big M equal to 5.4 kilograms hanging from two long cords. A bullet of mass little m equals 9.5 grams is fired into the block, coming quickly to rest. The block and bullet then swing upward, their center of mass rising a vertical distance of h equals 6.3 centimeters before the pendulum comes momentarily to rest at the end of its arc. What is the speed of the bullet just prior to the collision? So we're looking for the initial speed of the bullet. Now, the first thing that you want to ask yourself here is, what kind of collision is this? Is this elastic or is this inelastic? Well, what happens here is the bullet becomes embedded into the block. So this is an inelastic collision, all right? We still have conservation of momentum, but there's no conservation of kinetic energy. But speaking of energy, we can see that when the bullet hits the block, it's going to give it some velocity, and then it's going to swing upward to a certain height, and it's going to have a velocity of 0 up there. So what does that tell you? What are you going to use if you have an initial velocity and then a final height? It should tell you that you want to incorporate conservation of energy at some point as well. Okay, and what we're going to do is, because we know the height, we want to incorporate conservation of energy in order to find the final velocity after the collision, in order to eventually find what we actually want to find, which is the initial velocity of the bullet. Okay, so let's write down our givens first. Now we have, I'm going to call this M1 will be the mass of the wood block. So our M1 is mass of the wood block, which is 5.4 kilograms. And then we also know I'm going to call M2 the mass of the bullet, which is 9.5 grams or 0.0095 grams. Sorry, kilograms. And then we know that this final height up here is going to be 6.3 centimeters or 0.063. So that's our height equals 0.063 meters, right? Now we want to know the initial speed of the bullet because it says, what is the speed of the bullet just prior to the collision? So I want to know I want to know V initial 2 equals question mark. Now, the other thing we know is that before the bullet collides with it, that block is just hanging there at rest. So my V initial 1 is going to be 0. So in order to find my initial velocity of the bullet, I need to find the final velocity after that collision. So final velocity equals question mark as well. And this is going to be the first thing that I need to find from conservation of energy, because final velocity after the collision will be my initial velocity for conservation of energy. Okay, so this is after collision. And this will be initial V for conservation of energy. Because again, that bullet's going to give it a velocity, that kinetic energy then becomes potential energy as that system swings upward. So first and foremost, we have to use conservation of energy in order to find that velocity. So I know that when that bullet hits the block, it's going to give it some kinetic energy. That's the only energy that I have in the initial case. When for the collision, that's really the final case, right? But so I have kinetic energy initial, and that will turn into potential energy final at the top of that swing. So I have potential energy final. That is 1/2 mv initial squared equals mgh final. Now here mass cancels out. Now if for some reason mass did not cancel out, this would be the mass of the block and the bullet together, because this is what has that initial velocity and then swings up to a final height. So if for some reason, like say there was a spring involved or something like that, and you had to use conservation of energy with a spring, we know that that potential energy is 1/2 kx squared. The mass wouldn't cancel out, and you would have to then use the mass of both of them as that total mass. But here it canceled out, so it's okay. If we solve here for velocity, we're going to multiply both sides by 2, take the square root. I get velocity is equal to the square root of 2gh. G, of course, is 9.8. So we get 2 times 9.8 times, and then our height was 0.063. And then I'm going to take the square root of that. So we get velocity is equal to, sorry, Rowdy. Rowdy is being rowdy. So here I end up getting velocity is equal to 1.11 meters per second. Now remember, this is the initial velocity of that conservation of energy portion of this motion, but it's going to be the final velocity of the collision, because this is kind of the velocity that the block bullet system has after the bullet collides with the block. So this right here will be V final for collision. So now we can do our conservation of momentum. Momentum initial equals momentum final. In this case, we have M1 V initial 1 plus M2 V initial 2 equals, and then of course M1 V final 1 plus M2 V final 2. But we know that since it's an inelastic collision, they stick together and the final velocities are the same. So we can use that inelastic collision equation, final velocity times the quantity M1 plus M2. So we know that I called M1 the block. So because of that, I know that the initial velocity of the block is 0. So this whole term cancels out to 0 because V initial 1 is 0. We are looking for V initial 2. So I'm just going to leave that as V initial 2. So M2 is the mass of the bullet. That was 0.0095 kilograms times V initial 2 equals final velocity, which is what we just found, 1.11 meters per second, times the quantity M1, which was the mass of the block, so 5.4 kilograms, plus the mass of the bullet, 0.0095 kilograms. So here we get 5.4 times 5.4 plus 0.0095. And then I'm going to multiply that by the final velocity, 1.11, and then divide both sides by 0.0095. And we end up getting the initial velocity of the bullet is 632.06 meters per second. And that's our answer.